So welcome along to the next of these videos called In Search of the Northern Lights. My name is Dr. Alan Wood. I'm a senior lecturer in the physics team at Nottingham Trent University. So let me just share the PowerPoint that we're going to be looking at today. There we go. So what have we been talking about already? Well, we've been talking about the Northern Lights, these beautiful bands of green and red and purple in the night sky. We've been talking about how their ultimate source is the sun. We've looked at how the sun triggers the solar wind and the solar wind triggers displays like this. We've talked about chemical transitions in the upper atmosphere and how these result in the green and red colors that we see so commonly. And yet we see green more often than red. And we've started to talk about why that might be as well when we talk about things like how does the human eye respond to different wavelengths of light? And at the end of the last video, I left you with a couple of questions. I said, how can we find the altitude of the base of the Northern Lights using instruments down at ground level? How can we do that? I left you with a second question. Why does the red aurora typically occur at greater altitudes than the green aurora? So why are the red northern lights typically higher than the green northern lights? And those are questions we're going to start off looking at in today's session. So to look at that, we need some instruments, and we're going to use a Meridian scanning photometer. Now this looks complicated, but actually it isn't. What a Meridian scanning photometer is it looks around the sky and looks for northern lights. Now, many of you will be familiar with the whole idea about how solar panels work. So, of course, we have sunlight instant on the solar panels, and that's usually converted into an electrical current. And so we get an electrical signal out from the solar panels. So what the Meridian scanning photometer does is it looks just at particular wavelengths, at the wavelengths of light associated with the northern lights. And it converts that information into an electrical current. And based on the size of that current, we can work out the intensity of the northern lights. Now, the Meridian scanning photometer can look at different places in the sky at different times. And the data looks a bit like this. It looks a bit confusing at first glance, but actually it isn't. I'm going to simplify it by just looking at this middle panel here. This middle panel refers to the green northern lights. So what we've got here is we've got time on the x-axis, and on the y-axis we've got position in the sky. So here we've got looking north. Here we've got looking straight up. Here we've got looking south, so looking to different points in the sky. And what this color scale means is it means how intense are the green northern lights. It's not telling us the northern lights are blue and then red and then green at different times. It's telling us the green northern lights at a wavelength of 557.7 nanometers are basically absent here. Here they're really bright all over the sky. Over here, they're quite intense, but just at one particular part of the sky. Here they're all over the sky, but not as bright as they were earlier. And so that's at 557.7 nanometers. We've also got other channels here referring to other wavelengths of light. And one of the ones which is particularly interesting is this one at the top, which are the red northern lights. And look here, if you compare the red and the green, you can see the patterns are slightly different. You can see the intensities are slightly different as well. So let's just focus on the green first of all. We want to find out the height of the aurora, the height of the northern lights. And to do this, the simplest way to do this is to use Meridian scanning photometers at two locations. So suppose we've got a Meridian scanning photometer here, and it sees the northern lights at an elevation of 60 degrees, looking northwards. Suppose we have a Meridian scanning photometer over here looking southwards, and it sees the northern lights at an altitude, at an elevation of 45 degrees. So we know that the northern lights are here. So now we just use trigonometry to find out their height. So let's work through that together. We might know how far these stations are apart. Just for example, let's say they're 150 kilometers apart. So at somewhere between those two stations are the northern lights, and they've got some particular height. We'll call that h. What we don't know is how far they are away at the ground from either observing station. So let's call this distance x, and let's call this distance y. So now we've got everything we need to solve this problem. So let's look at the trigonometry. So to start off with, we can say that the tan of the elevation at the left-hand station here, the tan 60 degrees, is going to be equal to the opposite distance over the adjacent distance. So from trigonometry, that's going to be equal to that height h divided by x. We can do the same sort of thing for the other observing station. We can say that tan, 45 degrees, because our elevation is 45 degrees, is going to be h, the altitude, divided by y, the horizontal distance. We also know that x plus y, these two distances here, equals 150 kilometers. We can see that from this diagram very nicely. So we've got everything we need to find h. And because we want to find h, the altitude, I've highlighted that in red. So we can begin very simply just by rearranging this equation. If x plus y equals 150 kilometers, well then x is going to be 150 kilometers minus y. We can then substitute in to our expression, we can substitute in for x into our first equation. So we get tan of 60 degrees equals h for height over 150 kilometers less y. And then if we want, we can rearrange this. We can rearrange this by multiplying through by 150 kilometers minus y and dividing by tan of 60. No problems there. We can now add y to both sides of our equation. So we've got an expression that looks a bit like this. We can then minus h over tan 60 from both sides of our expression. And what we've now got is we've now got an equation where y is the subject. So y equals 150 kilometers minus h over tan of 60. And I'll just take that equation forward onto the next slide. There we go. What else can we do? Well, we can rearrange our equation from here, tan 45 degrees equals h over y, to make y the subject. Excellent. So we can do that very nicely. So we've got two equations here where y is the subject. So we can equate them. And when we equate them, we get something that looks like this. 150 kilometers minus h over tan of 60 equals h over tan of 45. So, and there is, and so what we can then do if we want is we can add h of tan of 60 to both sides, and we get this expression here. There we go. So what can we do next? Well, next we've got these common factors of h associated with both these fractions. So we can just take out that common factor. So we can say 150 kilometers equals h, then multiplied by, in brackets, 1 over tan 45 plus 1 over tan 60. And we can now rearrange to make h the subject. Now h equals 150 kilometers over 1 over tan of 45 plus 1 over tan of 60. And we can evaluate this. We can find that h is 95 kilometers. Excellent. So we can find the height of the aurora. So that's our first question answered. We can now find the altitude of this. We can find the altitude of this green here. But then I asked the second question, why does the red aurora typically occur at greater altitudes than the green aurora? And of course, we could find this out by doing the same kind of analysis as we've just done using data from Meridian scanning photometer. But why does it happen? Well, we looked at this energy level diagram in the last session. And what we said is we've got material hurtling in from space, crashing into the upper atmosphere. And when it does, it excites the oxygen atom. An electron moves to an excited energy state. And we drew this diagram showing the electron moving to this excited state. And we can say it can drop back directly, as shown here, in which case we get emission at ultraviolet wavelengths, which we can't see, but some of our instruments can. Or we can have the electron dropping back to the ground state in this two-stage process with green and then with red. Now, we said it takes time before the electron drops back down to these lower states. We said the typical lifetime of this excited state here at 4.2 electron volts is 110 milliseconds. So if our excited oxygen atom collides with something else within 110 milliseconds, that energy is lost as heat. It's never re-emitted as light, so we don't get green northern lights. But 110 milliseconds is not very long, so that's not likely to happen. The lifetime of this excited state is 3/4 of a second, 0.75 seconds. That's much longer. So it's a greater chance that our excited oxygen atom will collide with something else and the energy will be lost as heat. So that's why we get less red northern lights than green northern lights. And we talked about that before. But also, let's think about what happens to the density of the atmosphere as we go up in altitude. So here we've got a plot showing density on the x-axis, altitude on the y-axis. As we go up in altitude, the atmosphere becomes less dense, markedly less dense, following this exponential curve. So that means if we're somewhere all the way up here, we've got small chances of collisions. If we're down here, we've got larger chances of collisions. So the further down in altitude we go, the greater the chance of a collision between our excited oxygen atom and the surrounding atmosphere. And that leads to a process called quenching. If basically all the excited oxygen atoms collide with something before we get light emitted, well then we never get light emitted. And for the green northern lights, this lifetime here of about 110 milliseconds, quenching occurs quite low down in the atmosphere, around about 85, 90, 95 kilometers, those sort of altitudes. And so we wouldn't get green northern lights below those altitudes. Now this state here has a longer lifetime, 3/4 of a second. So that means quenching occurs higher up in the atmosphere, and quenching for this excited state and for red northern lights typically occurs at 200, 250 kilometers in altitude. So it means we don't get red northern lights emitted below that because the lifetime of this excited state is so long. Our excited oxygen atom collides with something else first. Now, we're going to look at some other instruments now. So, we were thinking about the Meridian scanning photometer, which is a very, very nice instrument. But let's think about how the northern lights change across an evening. The Meridian scanning photometer only looks north, south, and straight up. If we take some images like these from a point-and-click digital camera, then you can see the northern lights changing beautifully across an evening. And this is this movie has been sped up a little bit. It's based on one frame taken every 2 minutes and expanded out to fill about 15 seconds of a video. So this means this has been somewhat spread up, but you can see how the northern lights are changing across the evening. You can see these beautiful east-west bands of colour across the sky. How can we look at these using a scientific instrument? Well, the instrument we're going to use is called an all-sky camera. So the all-sky camera observes the whole sky at once. Now that's the whole sky as seen by someone on the ground. So it's not the whole of the Earth, but if you stood somewhere, it'd be how far you could see towards the horizon. So these all-sky cameras sit in domes, rather like these sort of things, here shown at the Aurora station on Svalbard in the Arctic, and they can see towards the horizon in all directions. And we might get black and white images from them rather like this. So this is then showing which proportion of the sky is occupied by the northern lights at different times. So here, for example, we've got the light greys. Those indicate northern lights. These slightly darker greys here indicate times when we haven't got northern lights. And this circular region is the field of view of the instrument. But they also work in color as well, and we get beautiful movies like this. So have a look at this. We can see this movie taken across an evening. We can see a little bit of green at the edge of the sky. Then we can see the northern lights expanding across the sky. We can see the reds and the greens and the whole sky exploding in color. We see the patterns swirling and changing. We see the northern lights here. It's a phenomenally beautiful phenomena. You can see from this diagram the reds and the greens occurring at different places, and based on what you now know, we know the reds are going to be higher than the greens, and we can start to make sense of these patterns. It looks like the greens are sweeping down lower to us, and they really are. We can see this movie is taken across a couple of hours because you can see the star patterns moving as well. You can also see some little regions here, these oranges, these are clouds coming in across the sky. And it really is a phenomenally beautiful movie, this one. If you're lucky enough to see the Northern Lights for yourselves, you may well see something rather like this. It's such a lovely movie. We're going to see this one more time. So we've got the Northern Lights here, just at the edge of the sky. Then we see the whole sky explode in color. We see these swirling, twisting patterns. We see them going very bright, very intense, then more diffuse. One of the most phenomenally beautiful of all natural phenomena, and one we can now begin to understand. Now, if we look at the northern lights from space, we can see something called the auroral oval, the region where we're most likely to get the northern lights. And here is the auroral oval. Don't worry about what this is at the moment, but this is a plasma caused by photoionization. We'll talk about that in a forthcoming session. But for the moment, just think here about the auroral oval. Now, you can see here's the UK, here's Norway, here's Greenland. The North Pole is somewhere up here. The auroral oval is not centered on the geographic North Pole. So I have some questions for you. What is the auroral oval centered upon? Now, in a couple of hundred years ago, the Northern Lights were much more common above Scotland than they are now. So this brings us to the second question. Why are the Northern Lights commonly seen in different countries in different historical eras? So there's a couple of questions for you to think about there. And that's where we're going to finish for today. So thank you very much for your attention, and I hope you join me when we continue this on Thursday.